Dear students, in this video I'll provide the next standard formula which helps you to find nth derivative of product of exponential function and a trigonometric function. Product, nth derivative of a product we'll learn generally as a Leibniz theorem later, but this is a special kind of a product which involves exponential function and a trigonometric function, namely cos and sine. First, let us recall a formula which is, so this is the formula which we will be deriving nth derivative of e raised to ax into cos bx plus c, where a is a constant, just like a real number, 5, 7 or -1, something like that. B and C are also real numbers. X is the variable with respect to which we differentiate. So nth derivative of this product, how to find out? So before deriving this result, we have to recall these two results. How to find the value or the expression, how to simplify this expression in terms of a single cos. Here you see cos t is there, sin t is there. How to simplify this expression where a and b are any constants, maybe 1000, maybe 10,000, or half, or 12, whatever it is, they are real numbers. So if we have a sum like this, a cos t plus b sin t, how to express it in terms of a cos or sine? Here I have written it as in terms of cos. We require the expression in terms of sine also. For deriving that, to prove this result, we will be proving this result, which helps you to sum up this value in terms of cos with a number. Here is a number. A and b are numbers, means this is purely a number. Whole raised to half means it is square root of a square plus b square into cos of t minus tan inverse b by a, where a and b are given numbers like this. A comes along with cos t and b comes along with sin t, and if we have this sum, this can be simplified this as something like this. So that's a very important result which we will be applying while finding the nth derivative of this product. Okay, so let us derive this result now. So for proving that result, let's call a as some r cos theta and b is equal to r sin theta. If you take a as r cos theta and b is r sin theta, squaring and adding cos square theta plus sin square theta is you will be getting it as a square plus b square equal to r square. Therefore r will be equal to a square plus b square whole raised to half. And if you divide r sin theta by r cos theta, r will be cancelled. You will be getting sin theta by cos theta as tan theta, and the other side is b by a, from which you will be getting theta is equal to tan inverse b by a. So remember these two formulas. When you put a as r cos theta and b as r sin theta, r will be calculated in terms of a and b like this, and theta will be calculated in terms of a and b like this. So now this is the expression we have to simplify. This a is replaced by r cos theta and b is replaced by r sin theta. R is common, and r comes outside. Then inside you will be having cos theta cos t plus sin theta sin t. Cos a cos b plus sin a sin b, you know it is cos of a minus b. So here I take t as a and theta as b. So it is cos t minus theta. So what is r? R already is found out. R is found to be a square plus b square whole raised to half. And and theta we have already found out it as tan inverse b by a. So we have reached this formula. T minus theta, this theta is tan inverse b by a, and this is your r. Totally this is the r, so this is whole raised to half, up to r raised to half we have r, so it is r in the cos of t minus theta. So we can express this one like this. Now the same expression a cos t b sin t can also be written in terms of sine like this, a square plus b square whole raised to half and a sine of t plus tan inverse b by a. That you have to, can you prove this? That's a homework for you. Now let's derive that nth derivative result. Let y equal to e raised to ax into cos bx plus c. This is a given function. We have to differentiate this one, but while you differentiate, you have to apply product rule y1 is equal to e raised to x, and the derivative of cos, you know, it is minus sine of that angle into derivative of this bx plus c, that's b. So first function derivative, the second we have applied, plus, that's a plus for the product rule, second function, that is cos bx plus c, into derivative of e raised to x is e raised to x into a. Now you can see that here is e raised to x, e raised to x, that common e raised to x can be brought outside. So therefore y1 will be equal to e raised to x into, yeah, look at this expression. I am writing this as the first expression, a cos bx plus c, a cos bx plus c minus b sin bx plus c. So now this is in the form of that expression which we have in the first result, a cos bx plus c minus b sin bx plus c. If you put this as r sin theta, r cos theta, and this is r sin theta, you can write it as cos theta cos bx plus c minus, that minus will become, instead of minus you'll be having cos a cos b minus sin a sin b is nothing but cos of a plus b. Here a is bx plus c, and b is theta, that theta will be equal tan inverse b by a. Therefore e raised to x into r in the cos of bx plus theta. This is your y1. Now let's proceed for finding y2. y2 is, you have to differentiate this one. This r is a number which is a constant. We have to differentiate e raised to x into cos bx plus theta again. So you have to apply again the product rule. First function is e raised to x. Derivative of the second, that is cos, it is again minus. Bx plus c plus theta will have a derivative b. So first function in derivative of the second plus second function, that is cos of bx plus theta into derivative of the first, that is e raised to x, which is a e raised to x. Again e raised to x will come as a common factor, that I will be taking outside. After that you will be getting a cos bx plus c plus theta minus b sin bx plus c plus theta. Now again if you take this as r cos theta and this is r sin theta, one more r will come. That r with this r will become r square, okay, r square e raised to x in the cos of bx plus c plus theta will come, so it is plus 2 there. Now you have a pattern. For 2 this is like this. Now you can guess what will happen for 3. It will be y3 is equal to r cube e raised to x cos bx plus c plus 3 theta. So it goes on like that. So generally we have a pattern r raised to n. When it is n y and it is r raised to n e raised to x in the cos of bx plus c plus n theta. So this is the nth derivative. This r will be a square plus b square whole raised to half. Raised to n means it is a square plus b square whole raised to n by 2. E raised to x will remain as it is. Cos of bx plus c also will remain like this. N is the number of times you differentiate. This theta is actually tan inverse b by a. So this is the derivative which you have to remember like this. This is the formula which you have to commit to memory, which we will be applying later. So nth derivative of this product is a and b are playing a greater role. C is there in the expression, but a and b is to be applied for finding a square plus b square whole raised to n by 2 as well as tan inverse b by a. So this is the expression which you have to remember. As a homework, let me give you this as a homework, how to find the nth derivative of e raised to x in a sin bx plus c. With that, we end this video. Thank you for watching.